All right, and welcome back, everybody. So last time we talked about least squares problems, and we walked through a little bit of data fitting as an application. And this time around, we're going to go into yet another application of data fitting in a different sense now. And in order to kind of set this up, I wanted to walk you through a bit of an example. So my wife is an organic chemist, and oftentimes I will hear her talk about NMR spectra, and I'm kind of curious, what does that mean? And she tells me that she uses Fourier transforms in what she does. So I figured I would take that opportunity to kind of learn about what kind of work she does, and kind of interested to see how it relates to stuff that I do that we are actually learning right now. So here's the idea. So if we are chemists, oftentimes when we run reactions, we would like to produce some subject, some sample. We want to run a reaction and get some output, some chemical or collection of chemicals comes out of the reaction, and we would like to know what is in that sample so that we can compare this against theory and calculate yields and maybe try to figure out how to separate out certain reagents from others. And there could be multiple different pathways that produce different molecules, or there could be multiple pathways that produce the same molecule. But either way, we would like to be able to determine what is in the sample after a reaction. And what we typically do in a wet lab is we are going to kind of take some sand, effectively, some silica, and let our sample kind of filter through the sand. And this is called a column. We are going to column away the impurities, and we are going to distill what remains. So hopefully the thing that we created, the thing that we want to know is in our solvent, is going to be in the solvent after we've filtered out all these larger all the larger particulate matter. So what we're going to do is we're going to take that distilled solvent, and we're going to take that solvent and distill it away. So we're going to separate out the solvent from the remaining bits of the reaction. And typically there are a couple of different ways that we can determine what is in the sample after we run the column and distill away the solvent. And this is a collection of 3 different methods that are very common. First, we would use possibly mass spectrometry, or gas chromatography mass spec, or in this case, the thing that we're going to learn about, the thing that we're going to apply our linear algebra to, is in something called nuclear magnetic resonance, right? So there is a gigantic machine that is effectively creating a magnetic field of varying frequencies, and all of these different methods are here to detect atomic masses of the molecules in your sample. So it's not going to tell you exactly what the molecule is or what the molecules potentially are, but they are going to tell you how much these guys, what their atomic masses are, and you can kind of figure out from the output of the data in the NMR what masses correspond to which molecules. But let me tell you how we actually figure out those masses in the first place. So, a little bit of physics here. Think about nuclear magnetic resonance as trying to flip between 2 different equilibria, right? And what we're going to do is think about a pendulum, how there is an up state and a down state. And think of the down state as being a ground state, as a nice low energy state of the system that the molecules or atoms would like to fall into. And in this case, we're actually measuring protons. So protons like to sit in certain energy levels more than others, right? So they like their ground states. But if you put in enough energy into the system, you excite those protons and they jump into a higher energy state, right? So think of this as you're trying to balance that pendulum up high, but you have to feed it a certain amount of energy to do so. So what we can do with an NMR is put in a magnetic field of a certain frequency and strength, so as to shove protons into these higher states. So this is only going to happen if the frequency is at a particular, or if the magnetic field is at a particular frequency, and this is what's called a resonant frequency of the nucleus. Right? So what we are doing here is turning up a magnetic field from low intensity to high intensity to try to track which frequencies resonate with our molecules. So we're not going to be able to tune this up very smoothly if we want to make a measurement. So we have to do this in discrete intervals. So we're going to slowly bring this guy up from low to high frequency, from low intensity to high intensity, change the frequency by a discrete amount, and then dial it up from low to high again. But if we hit a resonant frequency, the field will move the protons from that low energy state into the higher energy state. And when we relax the intensity, these protons will fall back down into their ground state. When charges move, right, protons are positive charges. When a charge moves, we create current. And this is what the gigantic machine is doing, right? This is a huge, like 10-foot tall machine, and it's a good like 5 or 6 feet wide. It's a big cylinder. You need a ladder to drop your tiny little sample into the top of that machine. It's kind of fun. We actually have one at Pacific, so if you feel like checking out the chem department at some point in the future, there's a big window into this NMR room near the office, the administrative office. Go check it out. It's a fun little excursion to go and kind of take people who are touring the campus, or you're showing your friends what you do. It's a fun little thing to do on the side. But either way, moving charges are going to create current, and we can measure the current here. So as we change the frequencies, we can measure how strong that current is. Right? And this is what we'll wind up with. We'll wind up with some discrete sampling of what our current looks like for different frequencies, and what the strength is. So how do we analyze this signal? And the idea would be to project this signal onto prototypical frequency functions. So basically sines and cosines of given frequencies. So we're going to take that signal, feed it into some black box algorithm, and out pops the intensity of each resonant frequency. And you can see in this little plot here, this is exactly what you wind up with when you feed the electric field output, or the current output signal, into what's called a Fourier transform, or a fast Fourier transform, or discrete Fourier transform. We'll define all of these terms shortly, but what you get is a density of the resonance. So you'll wind up with an area under the curve telling you how many protons get lifted into this higher energy state at a given frequency relative to some unit. So basically, how many protons per molecule are being lifted into the resonance state. And across that x-axis, or the horizontal axis, we have something called the chemical shift. And this is essentially what happens to the frequency when we hit it with a Fourier transform and throw it into a new domain. We get this thing that we call the chemical shift. But you think of it as just a transformed version of the frequency. So we have created something here called an NMR spectrum. Right? And this is something that people are training to read right now. So like you have to have certain specialization in order to be able to identify what this plot is saying from a chemical standpoint. There's actually research going on right now. A good friend of mine is actually working on trying to use machine learning to train computers to read these NMR signals to identify the most likely candidates for which chemicals produced this signal. So definitely an active field of research, and something that you can look into for sure. Feel free to ask if you want to know what my friend is up to. But let's see. We have produced the NMR spectrum, and our first question is, how in the hell did we go from our voltage, or our current signal, into this NMR spectrum? And the answer is that we are projecting this signal onto some trigonometric function space. And our job now is to build that black box. So what we have here from an abstract point of view is some transformed, some signal, right? And I'll call this F tilde. And it's going to be stuck between points A and B on some horizontal axis. And we're not going to be able to figure out what this function looks like at every point along the interval from A to B because we're in a computer, and computers only have a finite amount of memory that we can use. The signal here is going to be sampled at n points, and we get to choose n. Right? It's easiest for us to space these points evenly along the interval from A to B. So we'll have, just like we did in Calc 2, we're going to space these guys out in even subintervals, and that looks like a very familiar formula to us. It's the length of the interval divided by how many subintervals we want, and we'll call that delta x. We are then going to transform the signal from AB over into 0 to 2 pi. So we are going to change the domain specifically. So we're going to shift everything down onto the 0 to 2 pi interval. Why? Because we're using sines and cosines of given frequencies. And these will be integer frequencies, and all integer frequency sinusoids have this 0 to 2 pi interval in common, right? It's just counting how many times, the frequency is going to count how many times the signal oscillates between 0 and 2 pi. So we're going to use the 0 to 2 pi interval so that we can go around a circle. And label our subinterval ticks as xj's, so 2 pi j over n will be what each one of these guys looks like over the interval from 0 to 2 pi. And this produces a sample vector, right? If we look at all the red points and figure out, okay, what does our function look like on this transformed domain? So again, we're trying to create a projector, so what are we going to project onto? I suggest that we don't really need to choose between sines and cosines. In fact, we are going to use both of them simultaneously, right? Sines and cosines are both important here, and we need to have both. So, fact, if we don't already know this, this is Euler's formula, right? So this, or Euler's, Euler formula. There's also an Euler identity that comes from this. E to the I times pi is equal to minus 1. That's Euler's identity. But this more general expression, this more general equation is called Euler's formula. And this allows us to consolidate sines and cosines into one function, but the thing is that these are going to be complex functions. Cosines will deal with the real parts, sines will deal with the imaginary parts. And you can actually check this formula. There's a nice derivation of it if you use Taylor series. Just group your real and imaginary terms. You should recognize the sine and cosine Taylor series, or since we're centered around 0, they're Maclaurin series. But what we're going to do is we are going to take theta to equal j times x, so that we wind up with combinations of sine of jx and cosine of jx, right? So j will act as a frequency, or an index for the frequency. But again, we're going to need to use complex valued scalars in order to do this. So we should use an inner product space that deals with our functions. So our functions come from continuous functions on 0 to 2 pi. And we're going to use the L2 inner product in the complex sense. And we're going to try to project onto this e to the I omega x function set. And we're going to treat it as a kind of basis. So if we haven't seen complex inner products before, which I may have mentioned at one point in time, but it's definitely worth addressing again, the complex inner product space, the L2 inner product space, it needs to use a variation on what we've been doing for real inner product spaces. And the big difference, what's not the only difference, is this negative sign. So what we have to do in general, let me scoot this over. If I wanted to take the inner product of f and g in a real inner product space, all I have to do is multiply the two functions f and g together and then integrate the result from a to b. But if I'm in a complex inner product space, then one of these guys needs a complex conjugate over them. And for right now, I'm going to go ahead and say the complex conjugation occurs on the first function, f. You can do this so that it's on the second function, but the point is that you should do it on exactly one of these functions, but not both. Right? To see why, feel free to ask me during class. But I will go ahead and just take this on faith right now that we have an inner product that works in a complex inner product space. All right. So what happens if I take the inner product between two different basis functions here, e to the inx and e to the imx? Well, you've done a homework problem very similar to this, and you've seen that these guys spit out 2 pi if m and n are the same, and 0 if m and n are different. And m and n are supposed to be any real number, but we're going to restrict our frequencies down to integers so that we can use 0 to 2 pi as our domain. But the point is that this works for any m and n, so that this collection of functions is actually an orthogonal set in our complex inner product space that we would like to use. All right. So with that in mind, let's come back to our sample. We would like to sample this this voltage curve or this current curve, and then figure out what does this look like, or when I project this function onto the complex inner product space that uses integer frequencies for e to the inx. So for n sample points, I'm just going to go ahead and say, oh shoot, I should be careful. It should be, yeah, oh yeah, but these guys repeat. That's okay, that's the whole point here. I would like to project onto all of the potential frequencies that I use, but notice that these guys start to repeat after a little while. Specifically, when j is equal to n, then notice what happens. I wind up with this particular frequency here, and there should be an x in there as well, an x, there it is. There. No, x, oh, x was that, yeah, okay, yes, of course. Shame on me. Do and do. Okay, so I'm going to go ahead and say that we are dealing with a specific location or specific frequency here. So e to the I times 2 pi j plus n over n, you can go ahead and distribute the multiplication in the numerator, separate out into two different fractions, and you wind up with two different terms, one of which, this guy right here, based on Euler's formula, gets me cosine of 2 pi plus I times sine of 2 pi. And scholars of trigonometry can tell me that this is 1 plus 0 times I, which is just a 1. So that means that if I shift by n here, so n integers later, I'm going to get exactly the same reading as n spaces before. So we can really only distinguish n of these functions. All right. So based on our samples, we can only distinguish n different trigonometric functions here. Oh, shoot. We can only distinguish n of these guys. And yeah, that actually, I really should put a k here to distinguish it from the n with the number of samples. So ikx, and k is an integer. But these guys start to repeat after a certain point. There we go. Cool. Or maybe a j to match the other notation. But anyway, we're only going to need to use n of these guys because we're only using n sample points. So we really can only distinguish that. So for Bn, or beta n, equal to this basis, this particular collection of functions, we're really looking at the n-dimensional shadow of the signal in that subspace of the complex inner product space. So our goal here, our eventual idea, is to project the signal, the electrical signal, as an n-dimensional sample vector approximation of f. And this means that our sample function f is exactly equal to some linear combination of e to the I kx, where k goes from 0 to n minus 1, because if I go to n, I will start to repeat. And this thing in the red box is called the discrete Fourier transform of our signal. And from the projection, from projection formulas, we know that our coefficients can actually be computed specifically as 1 over 2 pi times the inner product of f and e to the I kx. So this is the derivation that we'll take for the discrete Fourier transform. And we'll go ahead and start applying this and see what it looks like, or how it works exactly for an actual signal.